There you go. So first and foremost, I want to go over the quiz. So I can see that most of you have selected the right answer. This is, well, maybe this is the worst in terms of correct answers, but I think the rest of them, it looks like evident. So heat pumps run on electricity. Yes, so the lesson I posted, it's the first lesson on the two kinds of systems we're going to work with. We're going to work with heat pumps or electricity systems, and we are going to work with hydronic systems that are systems that burn fuel and then heat up water, okay? So we can we heat up water with electricity? Yes, we can. But the most effective way to heat up water is first solar. If we use solar collectors to heat up water, this is for free, and this is the most efficient way. The second most efficient way is by burning gas. Burning gas, it's a quite good option to heat up water. So for heating system, gas is a good option. And finally, we can heat up water using electricity, but it's not as efficient as the solar or as the burning gas methods. The good thing of electricity is that if we connect our electric device, the heat pump, with solar collectors, with PV panels, photovoltaic panels, then we can use the electricity that we are generating at home to run our electric devices. And that's perfect because we are closing the cycle. So we generate electricity, we use the electricity we are generating to run the devices we are using at home. So that would be perfect. Sometimes we can't do that, or sometimes we need a backup, because if we don't have any sun for a couple of weeks, what do? We need a backup. So it's very unlikely that we can have only a full PV photovoltaic system with batteries or with electrical devices. So we always need a backup generator, and this backup generator can be by burning some fuel. Okay, so we have to combine different things. Anyway, heat pumps, it's something that runs on electricity, or heat pump, it's something that runs on electricity. And running on electricity, we can heat up and we can cool down. So the only way we have to cool down or the air conditioning or the cooling system is by using electricity. We cannot cool down anything by burning fuel, in theory. We can, but it's very complicated. So in buildings, the only way we have to cool down buildings or to work with the cooling system is by using heat pumps running on electricity. Okay, so first, heat pumps run on electricity. Yes. Air handling units, and this is the most important thing on this lesson. We have to understand the difference between heat pumps and air handling units. An air handling unit, yes, are usually placed on the roof, but air handling units, it's something that ventilates space. So we need two things. So when we are talking about mechanical systems, we need to we need heating. So what can we use to heat up space? We can burn fuel. That we can use solar collectors. What else? We can use heat pumps. Heat pumps with electricity. Okay. Usually, mankind has been burning fuels over the last 2 centuries, and we have created a lot of issues. Okay, so we have to stop burning things, And what can we do? We can use solar collectors. Yeah, and it's important to understand the difference between solar collectors and photovoltaic panels. I know that I'm going over things that we saw or we learned in Arch 260, but I think it's worth going back again. So if we are talking about solar collectors, those are the kind of panels that heat up water. Okay, so this is a typical solar collector. So we have a water inlet, a water outlet somewhere, and then we have a coil. A coil, it's a pipe that is bending so that the inlet is cold water, and then the sun strikes on this surface and heats up the water that is running through this coil. And then at the outlet, we have hot water. It's very basic, and this is a solar collector. If we are not talking about solar collectors, if we are talking about photovoltaic panels, photovoltaic panels are different. So first, we don't have an inlet or an outlet because the water is not running through these photovoltaic panels. And as you can see, they are different. So solar collectors are like this. We have this coil, so we run water through the collector. With the photovoltaic panels, we have those cells, those photovoltaic cells, those black squares or rectangles, and they generate electricity, but it's completely different. So when we are talking about solar energy, the first thing we have to differentiate between solar collectors. With solar collectors, we heat up water, that's it. With photovoltaic panels, we can generate electricity. So please, solar energy, it's general. So we have to specify. If we are talking about electricity, we have PV panels. If we are talking about heating up water, we are talking about solar collectors. So that's the first, okay, so by heating, if we need heating, we can burn fuels, we can use solar collectors, and we can use heat pumps. So we can use heat pumps on heating mode, and it works. If we are working about cooling, we cannot burn fuels. We have to use heat pumps. And that's it. There are other systems, but I don't want to write it down because it's too complicated. And it is the solar cooling. Okay, the solar cooling. First, we need a lot of solar collectors. And with these solar collectors, we are generating a very high temperature. So with this very high temperature, we can activate this solar cooling machine or solar cooling engine. Is it used in buildings? I have seen this in a couple of buildings, and all the architects and engineers that have been working with this system, they told me, okay, I won't do it again. Don't do it. I did it because we were young and unaware, but please don't do it. In theory, it's very efficient. It's incredible because we can use solar energy for free to generate electricity. But it can work in this kind of plants. We can have solar thermal plants. Yeah. So, I mean, at a big scale like this, it looks cool. Okay, so here we have a lot of solar, a lot of mirrors oriented to that point. So all the reflections of these mirrors are just meeting on this point. So the temperature that we generate here at this point, this tower, it's extremely, well, it's very high. So we can generate steam and electricity. Okay, so In this case, this solar cooling or this solar way to generate electricity, it works. But in buildings, we can't do this. Okay. Anyway, we are not going to use, or we're not going to study these kind of things because this is not for buildings. Maybe it's a solution for at a big scale for cities or for neighborhoods, or maybe this kind of solar thermal plants can work. But in buildings, we're not going to study this kind of. Okay, so for if we need cooling in our buildings, we have to use a heat pump. We have to use a heat pump, and that runs on electricity. And yeah, we can use PV panels, photovoltaic panels, to produce electricity. Okay, the PV panels produce electricity. They are not a cooling system. So a PV panel doesn't cool down whatever. No, it produces electricity, and then we can use that electricity to run a heat pump, and we can use that heat pump to cool down the building. Okay. But heating, we have a lot of options because we can burn fuels, we can use solar collectors, or we can use heat pumps. For cooling, we only can use heat pumps. We don't have any other option in building. And finally, we have ventilation. So if we are working with ventilation, we can use natural ventilation. Ventilation. What is natural ventilation? Opening windows. So if we open a window, we ventilate rooms. Or so usually the natural ventilation, we can't use natural ventilation in commercial buildings. We need a mechanical ventilation. We can use natural ventilation at home, in single family houses, small buildings. Or we can use natural ventilation as a strategy to save energy in other buildings that have a mechanical ventilation. If you are in our TDS center, you can see that there are only a few windows that you can open. I think in some classrooms you can open the windows, but if you are in the lobby, you can't open windows in the lobby. So it has a system, it has a mechanical ventilation system. But I don't know if you have been there, because some of the windows that are openable are mechanically operated, and when there are some conditions outdoors and indoors, some of the windows open, and they allow fresh air to enter the building. But it's controlled, so it's not okay. I feel like opening a window. I can't do that in the TDS center. This is a natural ventilation because I'm just opening windows, but it's a natural ventilation that it's controlled by an electronic control unit. That, okay, when we have optimum outdoor conditions and we have these indoor conditions, then the system opens the window. So the user, the people, are not allowed to do that. Any questions? No. Okay, so we have natural ventilation for single family houses. We can have mechanical ventilation. And for commercial buildings and office buildings and schools, so when we have a high occupancy, every building it's not a residential building, we have to use mechanical ventilation. So for mechanical ventilation, we have two devices. We have a heat recovery. You should know what a heat recovery is. And we have the air handling unit, which is AHAAU, air handling unit. Okay, so this is it. If you know this, you know 90% of the mechanical systems that you can find in buildings. We need a heating device. It can be a gas boiler or an oil boiler or a pellets boiler, or we can use wood, whatever, but we have to burn something. Or we can use solar collectors if we want to heat up water, or we can use heat pumps with electricity. So we have three options for the heating system. For a cooling system, we only have the option of the heat pump. And for ventilation, we need natural ventilation in residential buildings, and we need mechanical ventilation for the rest of the building. And we can use, I mean, mechanical ventilation is now regulated, so we can, we have to, because with ventilation, we can have a lot of heating or cooling loads. So we need a device that controls the temperature for this mechanical ventilation. So we can use heat recovery, or we can use air handling units. It's an air handling unit, it's a big heat recovery, or it's a heat recovery that has other options. Okay, but those elements recover heat from the indoor, okay, because we have indoor air at comfort temperature, and then we need fresh air. And if it's winter, fresh air can be at 20 Fahrenheit or 10 Fahrenheit, it can be very cold. Okay, so we have to mix the outdoor air and the fresh air. Okay, we have some friends that are using the chat. Well, I don't understand, and I better don't understand. Okay. So let's continue. We have all these heating systems, and what we are going to explain, well, we were explaining this because we were going over the test. There you go. Okay, so that's the difference between heat pumps and air handling units. Air handling units, it's something that ventilates, or we use air handling units to ventilate buildings. Heat pumps, we use heat pumps to produce either heating or cooling energy. So that's the difference between heat pumps and air handling units. Air-to-air split systems. Well, the air-to-air split system run on electricity and can provide heating and cooling. That's it, because the split system, it's a system that works with a heat pump that runs on electricity. And then we need because heat pumps are placed outdoors, and then we need an internal unit. It's the one that it's providing us with the air at the right temperature. Okay, so if we look at what the split system is, there you go. Those are split systems. Okay, so we have this element. This is the exterior unit. There are two exterior units here. And then we have the indoor unit. Okay, so this is the split system. This is the outdoor unit, and this is the indoor unit. And we have a remote. And they are connected by some pipes. We will talk about this. But this is a split system. This is a heat pump. The heat pump is placed outdoors, and this is the internal unit placed indoors. But the system itself, the split system, it's this plus this. It runs on electricity. Both units run on electricity. The heat pump runs on electricity, and the indoor unit runs on electricity. And so the question was, air-to-air split systems run on electricity and can provide heating and cooling. Yeah, this is a heat pump, and a heat pump can provide heating and cooling. Ventilate indoor spaces. There are 21 or 20%, 21% of students that thought that air-to-air split systems can ventilate indoor spaces. No, air handling units can ventilate indoor spaces. Okay, but the split system, or the air-to-air split system, it doesn't ventilate because it doesn't allow fresh air to enter the building. It cools down the air inside the building, but it doesn't interchange indoor and outdoor air. This is, it might sound complicated, and it is, and it took me years to get used to all these things. But we will be speaking about this many times, so at the end, I hope you can internalize all these elements, okay? The air handling unit, the heat pump, the air-to-air split system. So there are different ways to name these three aspects, the heating, cooling, and ventilation. So be careful, these 21% of students, air-to-air split systems, a split system does not ventilate indoor spaces. Air handling units do it. Then we have a VRV, that stands for Variable Refrigerant Volume Multi-Split System. A multi-split is a system that has more than one split. So this is not a multi-split system because we have an outdoor unit and we have an indoor unit. This is a multi-split system. For example, we have the same outdoor unit and we have different devices connected to this outdoor unit. So that would be a multi-split because we have different indoor units, okay? When we have only one heat pump, one indoor unit, this is not a multi-split system. Yeah, so those are examples of multi-split systems. We have different indoor units connected to the same outdoor unit. So here we are talking about multi-split systems, and we are talking about the variable refrigerant volume. Okay, so use variable control to provide customers with the ability to maintain individual zone control in each room of a building. This is something interesting because if we are talking about multi-split Yep, there you go. Okay, so we can have just an outdoor unit. Okay, so this is the outdoor unit here. And we have three different elements, 1, 2, 3, in three different rooms. If we are working with a variable refrigerant flow, that's very useful because we can turn on this element and the heat pump is working only with the flow that this element is demanding. If we are working with two elements, this operates at the rate that these two elements are demanding. Or if we are working with the three elements, we can work with three different conditions. Nowadays, all multi-split systems use this variable refrigerant flow. I think so. But we can find in buildings that are more than 10 years old, we can find multi-split systems that are not variable refrigerant volume. So that means that imagine that only one of these units is on, so the heat pump is working at full capacity. They can't adapt the electricity consumption to the demand. Okay, so I have dimensioned this for these three units, and if I'm using only one, if I don't have this variable refrigerant volume, the heat pump is consuming a lot of energy. Again, now I don't think we have to specify that we need this kind of system, but you can find multi-split systems that don't have this variable refrigerant volume. And there's something we tend to mistake because there are a lot of acronyms, VRV. There another one that is the variable air volume.
Fernando, what was the unit in the middle between those three units that you were just showing?
This one. This.
Yeah, the middle one. Yeah.
Okay. So you mean this one, and that one?
Or no,
okay.
No, the one you have. Yeah, the one you're mousing on right now.
This one. Okay. So they are interior units. That's an interesting question because this is the heat pump. So we all have seen those heat pumps because they are outdoors, and yeah, we can see this. And then I'm sure that you have seen this many times hanging on walls. You have seen many times units like this on false ceilings. If you go to the TDS center, if you go to the office spaces, all the offices are, they have this kind of units. You can see this kind of units, especially in residential buildings. And these units, it's the same, but they are hidden in the false ceiling. So you haven't seen this before because buildings with this kind of units, those units are hidden above the false ceiling. And then you have a small duct to conduct the air to a grill.
Oh, okay.
So we can have three kinds of indoor units. We have these units that are hanging on walls. We have these units on the false ceiling, but we can see this. And then we have these units, but these units are not visible because they are hidden. Okay.
Okay, thank you.
Thank you for the question because yeah, I forgot to mention that we can have this kind of these three kinds of internal units. Okay, what else? Oh, I was talking about the variable air volume. Yeah, so there's a variable air volume which is VAV versus VRV. Okay, so variable air volume, we will hear about this. This is for air handling units. Okay, so this is the variable air volume, VAV. So we use this for ventilation. And it's the same concept. We are ventilating different spaces and we can apply this flow that we need to the space that I'm using. So imagine that in the TDS center, we have different classrooms. So some classrooms are occupied and some classrooms are empty. If I have only one air handling unit without this variable air volume, again, if I am working with one of the classrooms, this element is working at the full volume. If we have the variable air volume, we can differentiate the volumes that we are applying or we are supplying to each classroom. But again, sometimes we say VRV, VAV. What is this? Okay, VRV, it's for heat pumps, and it's related to the refrigerant. If the refrigerant is the gas or the liquid, the fluid that connects the heat pump and the indoor unit. When we are talking about variable air volume, we are talking about air handling units, and we are talking about air. We are not talking about, yeah, we're in the other one, VRV stands for refrigerant, and VAV stands for air. Okay, so this is for ventilation. The other one is for heat pumps. We will mention this every single day. So at the end, I hope we will all become familiar with this. Ground source heat pumps. Okay, so this is a different heat pump. So we can have air heat pumps or ground source heat pumps. So if we have air to air heat pump, this is it. Okay, why air? Because we have this fan, and this fan is rotating, and it's refrigerating the oil that goes through this grill. Okay, so it's in contact with air. But if we look at ground source heat pumps, yeah, so those ground source heat pumps, yeah, they are something like this. So they don't have a grill and they are inside the building. Okay, so the air heat pumps, they are outdoors because they need to interchange heat with the surrounding air. But ground source heat pumps, they don't work with air. They work with underground water. So this is it. So we have the heat pump here inside the building, and then we have pipes that are buried in the ground. So they don't have to be in contact with air, those ground source heat pumps. Okay. So that's different. What was the question? The ground source heat pumps can be used with radiators and radiant floors. Yet, because those ground source heat pumps, they heat up or they cool down water. So if we heat up or cool down waters, we can use radiators and radiant floors. But again, if we are working with this kind of pumps, we need the outdoor units and we have the indoor units. Yeah, so here, I think in this picture, we see this. So this is the heat pump. Okay, so outdoors, buried, underground, we have those pipes. And the heat pump is connected to these pipes here. And then the heat pump is connected to the systems that we have indoors. It can be radiators or it can be a radiant floor, okay? So those pipes here are buried outdoors, and those and the terminal units or the radiant floor or the radiators are indoors, and the heat pump connects both this one and that one. Okay, but a ground source heat pump, it works with water. So we have water outdoors and we have water indoors, and we heat up or cool down the water indoors. Okay, so air-to-air heat pumps, we work with this split system. We have these outdoors and we have these indoors. So this indoor unit is working with air. It doesn't work with water. It works with air. But this ground source heat pump works with water indoors. Okay, so there are different terminal units. The terminal units here are those splits or indoor split units. And the terminal units here are either radiators or radiant floors. Again, it's complicated, but it's, there are only 2-3 systems. So when this is the first day, we are talking about this, but after a couple of weeks, I think we will become familiar with all that. And then you will have to connect things. I will provide you with different systems, and then you have to connect those systems. So I will teach you how to do this next week. Anyway, ground source heat pumps, they can be used with radiators and this. They can't ventilate indoor spaces. Ventilation, it's about air handling units. When we have heat pump and ventilation, they are not in the same sentence, okay? So heat pumps do not ventilate indoor spaces and are usually placed on the roof. No, because as you can see, the ground source heat pump, it's usually placed on the basement, okay? The air heat pumps, these kind of units, we can place these kind of units on the roof or on the wall. But the ground source heat pumps, they are never placed outdoors. They are always on the basement. They are not on the roof. Okay, so we have air to water and water to water heat pumps. Wow, what is this? Air to water and water to water. Okay, can be connected to solar thermal collectors to produce domestic hot water. This is correct because air, we can have different kinds of heat pumps. Heat pumps. We have air to air. We have air to water. And we have water to water. Water to water heat pumps are the same as ground source heat pump. And then we have air to air and air to water. What's the difference? These When we are talking about split systems, this is an air-to-air heat pump because it's outdoors and it's in contact with outdoor air. And then the terminal unit is something that heats up or cools down air. So this is an air-to-air heat pump. We have air outdoors, air indoors. Air-to-water heat pumps okay, if you look at them, the air-to-air and the air-to-water heat pumps, they are the same. So if you look at them, you don't see any difference. But if you look at the schematics, then the air-to-water heat pumps are connected to radiant floors, radiators, fan coils, that is another terminal unit that runs with water. And it can be connected to solar collectors. Those are solar collectors. So we have the air-to-water heat pump. This air-to-water heat pump is connected to a tank, and this tank is connected to those collectors. Okay, so those solar collectors can heat up the water of this tank, and then the water of this tank is distributed inside the building. Or if we don't have any sun, the heat pump is heating up this tank, and then the hot water is distributed inside the building. Okay, so this is the difference between the air-to-air. Air-to-air works with these split systems. We have air outdoors and we have air indoors. Air-to-water, we have air outdoors, but we have water indoors. And water-to-water, we have water outdoors and we have water indoors. So that's the difference between these three kinds of heat pumps: air-to-air, air-to-water, and water-to-water. The three of them are heat pumps. So we have 1, 2, and 3. The three of them are heat pumps, so they run on electricity, they do not ventilate indoor spaces, but depending on if we have what we have indoors and outdoors, if we have outdoors and indoors, this is air to air. If we have air outdoors, water indoors, this is air to water. And if we have water outdoors and water indoors, it's a water to water or a ground source heat pump. That's important. This is one of the first decisions that we have to make. If we are using air-to-air, air-water, or air-to-air technologies, we have to assume that we are going to have these ugly units outdoors. Do you like it? Nobody likes it. Okay, so don't say, yes, I like it, because nobody likes it. And in these kind of buildings, yeah, so you have to place this here. Come on, it is ugly, it's terrible. Okay, so if as an architect, I see something like this, I feel miserable. So I feel that I have failed as an architect, because that means that our client is not comfortable and he has to do this. Okay, so if you are thinking of these kind of elements, please try to hide them, because they are not beautiful. You have to be in contact with air. But again, if our client feels that it's too cold or too hot, they will end up putting this in the middle of the outdoor wall. Well, I mean, I wouldn't commit suicide, but I wouldn't be proud of myself if something like this happens. But if you are working with this kind of technology, the air to something, air to air or air to water, you have to plan that eventually you will have this somewhere. Okay, if you have the ground source heat pump, you need a mechanical room. And this is something that you have to realize, that you need a mechanical room, because those kind of pumps cannot be outdoors. They have to be indoors. So you need a mechanical room. So on your basement, you have to dimension that mechanical room according to the size of the heat pump. Okay, so this the mechanical systems affect the design of the house. And if you are done with the design and mechanical engineers tells you, okay, but what do you want, an air-to-air or an air-to-water heat pump? You say, what? I don't know, air-to-air. Okay, so they place this on your facade. No, no, I don't want this. Water-to-water. Okay, so do we have a mechanical system? No, a mechanical room? No, we don't. Okay, so without a mechanical room, we cannot place water-to-water. So you have to make that decision immediately, and then you have to keep on designing. But making the decision, and there is not the right decision. I cannot, okay, use water-to-water heat pumps always. No, it doesn't work like this because it depends on a lot of things. Water-to-water heat pumps, they are much more expensive than the air-to-air heat pumps. So it's something that we have to deal with the mechanical engineer, with our client, because there are design decisions, budget decisions, and they are all affected by the mechanical system. Okay, so air-to-water heat pumps can be connected to solar collectors, and that's it. So this is the quiz. We are done explaining the quiz, and now I'm going to start this. We have to keep in mind all these things because everything is connected. And now we are going to talk about this, the psychrometric chart, but the psychrometric chart is connected to the heating and cooling system that we are working with. Okay, so it's not disconnected. It's not like, okay, I don't understand the psychrometric charts, but I do understand and I like heat pump. Everything is connected, and I will try to connect it today. I'm going to go over what a psychrometric chart is. Also, we saw this in Arch 260, so I assume that even if you have forgotten everything, but at least you have heard of it. You have heard of what a psychrometric chart is. A psychrometric chart is a way to assess comfort in our building. I told you that there are thresholds for comfort conditions. So we have 70 to 75 Fahrenheit in temperature, and I don't know, maybe 35 to 50 or 55 in relative humidity. So within this narrow or this small rectangle, we have to live. If our building is not within those limits, our clients won't be happy and they will feel uncomfortable. And feeling uncomfortable is something that you can't explain. You say, I don't know, I don't feel well here. Why? But I don't know. I don't feel well. And people can't explain that. Okay, so it's because either the relative humidity is too high, or the temperature is too low, or the temperature or the combination of the relative humidity and the temperature is not the right one. But everything is about relative humidity and temperature, and this is comfort. And there are other factors affecting comfort. For example, the clothes we are wearing. Yeah, but can we control this as architects, the clothes that people are wearing in our building? And no, but clothes are related to activities. If we're designing a gym or a sports facility, so we can assume that the clothes are different than if we are designing an office building, okay? So we need to be aware of that. But everything about comfort, it's about temperature and about relative humidity. So we can control temperature with the heating and cooling system. We can control the relative humidity with the ventilation system. So that's why in our buildings, we have to integrate both temperature, heating and cooling, ventilation, air handling units, or heat recovery. And after that, okay, so I have designed this, and I'm operating my heat pump in cooling mode. I'm operating my air handling unit at this flow. So if I'm operating this, what are the indoor conditions? Okay, so if I calculate indoor conditions, and they are within this comfort rectangle of the psychrometric chart, everything goes well. If they are out of these conditions, I have to either change the system or adjust parameters. And that's something that we are not doing as architects. But mechanical engineers, they have to adjust the parameters, the working parameters of the heat pumps, of the air handling units, because we have a lot of control options. And poof, this is a world that it's too complicated, and you have to rely, at the end, you have to rely on mechanical engineers because they adjust parameters. So you can decide the heating loads, you can decide the place where your systems are, on the roof, on the basement, whatever. But at the end, if you want to run all systems in the right way, then some engineer had to adjust all these parameters. It's complicated. Anyway, this is the, what is this? The psychrometric chart. And usually there are two things that we can control, or we can know, or we can measure inside the rooms. We can measure temperature. We all understand temperature. And we can understand relative humidity. And we have sensors. So in every single family house, or in every single room of a building, I'm sure that nowadays we have sensors for temperature and relative humidity. So we can see, okay, so this is a 72 Fahrenheit, relative humidity 50%. So you can go to this psychrometric chart, 72 Fahrenheit, 50. Is it within the comfort range? Yes, okay, that's fine. But there are other magnitudes that we have to be aware of in psychrometric charts. And those magnitudes are, first, the wet bulb temperature. If you remember, I know that you have to remember things that we saw that a year ago. A lot of things have gone on in a year. But we spoke about wet bulb temperature. Can you remember, or does any of you remember where or what we use wet bulb temperature for? I'm asking a question, so I assume.
Oh, I think the wet bulb temperature is the temperature like when everything in the room like is, I think it's like when it's like the humidity or something. And
I
then
remember you describing it like when you get out of the shower or something.
Yes. Okay. Yes. So at least you remember that I described something when I get out of the shower. Yes.
No, you said you said like it's the temperature when you're, well, not like you personally, but say I.
Oh, I think it's the temperature that you feel, even though like it's not.
You feel,
yeah, even though it's not that. Yeah, even though it's not like the temperature the room is.
There you go. It's not the temperature of the room. It's the temperature that you feel when you are soaked, when you are wet.
Yeah.
Mm-hmm.
Okay, and it's different because if you are wet, you feel colder than if you are dry. So that's the wet bulb temperature, the temperature we feel when our skin is wet. Okay, so this is the wet bulb temperature. But we used a wet bulb temperature to calculate something very specific, and this is the answer that I want to hear. Matthew, are you there? Matthew Griffin?
Yeah.
Yes, you are there. Come on, you should know. You should have heard this over the summer. So, what do you calculate with the wet bulb temperature?
Can you calculate with those?
What?
Can you calculate with those?
Calculate what? Sorry, again? Wait, I don't hear you, Matthew.
Hello?
Yes, now. You sound like you are in a spaceship. I know, are you there, or are you on Earth, or where are you?
We're using Grace's laptop, sorry.
Oh, don't throw shade.
Okay. Well, anyway, wet bulb temperature. We used it to calculate latent
heat.
heat. You remember what latent heat was? Well, you don't remember. It's perfectly understandable. But we had sensible heat and latent heat. So the sensible heat is related to the temperature, and latent heat is related to the content of moisture that we have. Okay, so go over those kind of those lessons. Well, I can explain this again, but sometimes I will talk about latent heat and sensible heat, and I assume that you know what I'm talking about. If you don't remember, please let me know, because don't hesitate to interrupt me. Okay, please, I don't remember what latent heat was, and whatever, and I will explain it again. Okay, I'm not going to explain what latent heat is today, because we're not talking about latent heat. But if you go over ARCH 260 lessons, if you remember the concept of wet bulb temperature, it's related to the latent heat. Okay, so we have ventilation load, and ventilation load, we have the sensible ventilation load and the latent ventilation load. And latent ventilation load has to do with the amount of moisture that we have in the air. So that's what, so anyway, we have this wet bulb temperature, and the wet bulb temperature is this. So if we have this point here, okay, this one. So this is the dry bulb temperature. Dry bulb means that it's not wet bulb. Okay, so the dry bulb is the temperature that we are used to. This is the dry bulb temperature. Then we go to with the relative humidity. The relative humidity are those curves. Okay, so if we move this way, up and leftwards, we have the wet bulb temperature here on this curve. Okay, so you see that here we have 0, 5, 10, 15, 20. Okay, so those numbers here, this is the wet bulb temperature on this curve. And there, okay, now if you remember, there were another magnitude that we used was the dew point. Do you remember the dew point?
Like, are you talking about what it is, or like what temperature?
Yeah, so if you have this point here, so this is the dry bulb temperature, and this is the relative humidity. Where is the dew point? Do I have to go upwards, downwards, left, right, or what do I have to do to calculate the dew point?
I can't remember.
Okay, you can't remember, so you are an honest man. Does anyone remember this?
I think so. To calculate the dew point, wouldn't you go from the point where the moisture content and dry bulb temperature meet, and then follow the diagonal dotted line up?
The diagonal line. Nope. It's easier than that.
Oh.
The dew point temperature is just going leftwards. Okay, so if we are here, if these are the indoor conditions, dry bulb and relative humidity, the dew point is just this one. If we go like this, this is the dew point. Why can't I? Okay, so from this point, if you go leftwards, this is the dew point temperature. So it's between 5 and 10 in this case, so somewhere here. Okay, so the dew point temperature is the temperature at which the water, the steam or the vapor gets liquid. So this is the dew point temperature. And that happens in windows. And it happens in windows because the windows are the coldest surfaces that we have in a room. Okay, so when we have a very high relative humidity and we have very low temperature in a window, it gets condensated. So water drops are on the windows. And in a psychrometric chart means that we are moving just leftwards, and at this intersection with the last curve, so this is the dew point temperature. Okay, so the dew point is related to the wet bulb temperature. So the dew point is the wet bulb temperature of a cold surface inside the room. So we can say that this is the definition of the dew point. Anyway, don't worry because we will repeat this many times. So this is the dry bulb. This is the relative humidity. If we go with this diagonal line going up, this is the wet bulb temperature. If we go leftwards, we calculate here the dew point, and the other magnitude is the moisture content. The moisture content. So we have to go rightwards. Okay, so with this blue line, if we go this way, this is the moisture content. And the moisture content, look at it's the amount of water that we have per mass unit. It can be a kilogram or it can be a pound in international units. In imperial units will be pounds. So it's the amount of actual water that we have in a unit of air. Okay, so it's not relative. It's the absolute value because the relative humidity, it's relative respect to what? Let's see. But the moisture content, and it's not only about moisture because we have water surrounding us. Most of the water is moisture. But if I have a glass of water here, and I have a glass of water, so this is part of the moisture content of this room. It's water, it's liquid water, okay? So this is the mass of water, vapor, liquid, and solid. We can have ice cubes, okay? So all this is part of the moisture content of this, of a room. Again, we will explain that many times. We don't work with moisture content. Only if we are designing mechanical systems, we can work with moisture content. And the same happens with the wet bulb temperature. Okay, so those are magnitudes. Architects, we don't work with this kind of magnitude. We work with temperature and relative humidity. Yeah, but to calculate these kind of things, probably we will need to work with this, the moisture content and the wet bulb temperature. Anyway, all this, it's in this psychrometric chart. And I have included here definition for wet bulb temperature, the difference between dry bulb and wet bulb temperature, enthalpy. Okay, so that's important. And here we talk about sensible heating, sensible cooling. So in sensible heating, we are just modifying the temperature. We are not modifying the total content of moisture. So we can have sensible heating if we increase the temperature. We can have sensible cooling if we cool down the temperature this way. And before moving to the, okay, so here we have the difference between the sensible heat and the latent heat. And well, here there's another example. So with this psychrometric chart, we have this point. This point is the dry bulb temperature is 80 Fahrenheit. So this is 80 Fahrenheit. The relative humidity is 36. So 4 is relative humidity, 36. And then you can check all these. The wet bulb temperature is 62. So if we move this way, we have 62. The dew point temperature is 50. So if we move this way, 3 is the dew point temperature. The humidity ratio, it's number 5. it's, we move rightwards, and then we have the humidity ratio. And well, and we have this enthalpy. Enthalpy, it's very interesting because it's the amount of energy that we have in this point. Okay, and I told you that we can't create energy from scratch. We can't say, let there be energy. Bing. We can't. It's a shame, but we can't do that. But we are surrounded by energy. And this enthalpy is the value of the energy that we have surrounding us in the air. Okay, so it's not, we can have electricity around us, but this is the enthalpy, it's the energy that we have in the air. So in this point, if we move, if this is 7, you see that this is 7, it's the same line that I used to calculate the wet bulb temperature, but this is the enthalpy. The enthalpy are all these dashed lines we have here. Okay, so this is BTU per pound of air. So this is the unit of energy that I have per unit of mass. Okay, so this is BTU per pound. Energy per mass. So in 1 pound of air that I have in this room, I have this energy. And then I can use this energy, or I can move this energy from this room to another room. But this is the energy that we have in the air embedded. We have energy embedded in the air of that room. So this is the concept of enthalpy. This is important because when we are cooling or ventilating or whatever, we are changing the enthalpy of the air. We are changing the energy. If we use the, look at this. This is the sensible heating. With the sensible heating, I move on a horizontal line from a temperature to a higher temperature. If I'm here and where am I? Look. There you go. Okay, so if this air, it's at this point, we have 80 Fahrenheit. This is the dry bulb temperature. If I heat up the air without introducing water, I move in this direction. And then I can get to 90 degrees. So by heating up the air, I increase the enthalpy. So the enthalpy here is, okay, this is 25 and this is 30. So in this point, I'm between 25 and 30. So the enthalpy here can be 27 point something. And the enthalpy there will be 30 because I have moved this. So I heat up the air and I increase the enthalpy. I increase the energy that I have in this room. If I cool down the air, I decrease the enthalpy. Okay, so the enthalpy is related to the temperature, but it's also related to the water content. So there are a lot of things to learn here. But anyway, when we are cooling down or heating up the air of a building, we are changing the enthalpy. We are changing the air, the energy embedded in our air, in the air we're breathing. This enthalpy, it's quite complicated. I mean, it's not easy to understand. We are surrounded by energy, and we can increase or we can decrease that energy by heating up or cooling down the air. Anyway, I told you that we can use the old-fashioned psychrometric chart, or we can use the 21st century psychrometric chart, and this is what we're going to do. Okay, so we have this free online interactive psychrometric chart. I will share with you the link. Ah, it's already here. Okay, so it's in that lesson. So if you just copy and paste this link here, you will end up on this website. And I told you that that worked only with international units. Nope, because here you can go to settings, and now you can use the English or imperial units. These are the international, these are the imperial units. So you can click here. This is not enough. You have to reset all inputs based on units, and then you have to submit. And now we have, yeah, this is Fahrenheit, and those are imperial units now. Okay. So you have to click here, input data for air properties, and here you can change the parameters. So let's say that this is 70 and 30. We submit, and there you go. This is the point. It's 70 Fahrenheit and 30% of relative humidity. But the beauty of this psychrometric chart is that here we have the dry bulb, we have the humidity ratio, it's 4.6. So if we go horizontally here, yes, this is between 4 and 5. So this is 4.6. The wet bulb temperature, if we go that way, the wet bulb temperature is 52. The dew point, if we go this way, that would be 37. Where's the dew point? Yeah, sorry, 37. Okay, so look at this. I go in this direction, and then this is the intersection, and I go down, and that's 37. So this is the dew point. Okay. And this is the enthalpy. The enthalpy, it's 21.9 BTU per pound. So if I move in this direction, yeah, this is close to 22. So it's 21.9. Okay, so with this, oh, and I think this is another option. You can click somewhere in this psychrometric chart to submit. And well, I don't know. Anyway, this is it. It's very useful because if you change conditions here, okay, this is 80 and this is 40. Just click input data for air properties and then submit, and there you go. You are in this point and you can access all this information. So you don't have to do this or go up or go, no, you have all the values here automatically. Okay, it's very useful. But it's not, we are not using this psychrometric chart just to, okay, so this is the point, or what is the enthalpy of this? No, we're going to use this to work with air handling units. Okay, so you see these small schematics here. So in these schematics, we have the fresh air. So this is the outdoor air. This is the temperature or the room conditions. And this is like an air handling unit. So we have a heating coil, a cooling coil, and we have a fan. So with this tool, we can control here the indoor dry bulb temperature. So it's 77. Now let's say it's 74. The indoor relative humidity, let's say it's 45. And then outdoor, the outdoor temperature is 95. That means that it's summer, and the relative humidity is 65. Okay. So if we calculate this, well, what do we have? Well, we have the solution to this problem. Okay, probably you don't understand what we have here, but it's amazing. If we have to calculate this by hand, it'll take hours. But with this tool, we can calculate this very easily. I will explain what this means, all these arrows or these dots, where there's something that we can understand easily. So the first one is the dry bulb temperature. So this dot here is 74 and 45 relative humidity. So this is the indoor air conditions. This is the outdoor, so it's 95 and the relative humidity 65. Yeah, so this is 60 and this is 70, so this is 65. So we're using this air handling unit to provide our room with fresh air. But at the same time, you see that we are using part of this return or part of this air that we are moving out of the building or out of the room, but we recirculate this and we mix the fresh air with this return air. And this is what an air handling unit is. An air handling unit is a box in which we mix different air flows. And this is what we're doing here. And then we have a heating coil or a cooling coil. And I have all these, this is the vent. So we have the conditions of the fan, we have the heating load, we have the moisture content that we are applying. So we have a lot of information. So it's too early to understand this, but I didn't know this tool, and I have discovered this tool last week, and now I'm very happy because I think now I can teach you this, because I didn't want to give you a lot of formulas, and I don't want you to make a lot of calculations. But here you don't have to make calculations. You only have to type the inputs, and with the inputs you will have the right answer. And what is our goal? The goal is this. You see here we have a cooling load and a heating load. So our goal is to make these two values as low as possible. Okay, so that means that we will work with different parameters, different inputs, and immediately we can see if we are improving the system or we are doing the other way around. Okay, but now it's quite easy. So in a couple of weeks, we will go back to this psychrometric chart, to this website, and we will use this website to calculate heating and cooling loads in Windows. And it's not about, you don't have to calculate anything. You only have to place the right inputs to get the right answer here. And there's another thing. This is online, and you will use this for the final exam. Okay, so make sure that you all can access this website, and I want you to practice a little bit with this website, and that's why I'm going to post an assignment, another small assignment at the end of this. Yeah, there you go. Okay, so you have here different examples, 1, 2, 3, 4. So I want you to use that tool, and I want the answer to these questions. So here we have the moist air, the dry bulb temperature of 80 Fahrenheit, and the wet bulb temperature of 67. You have to find the relative humidity and the dew point temperature. Okay, so if you open this, we have to go to the basic option. And here we have the inputs. One of the inputs is the dry bulb temperature, and the other was the wet bulb temperature. So you have to select here wet bulb temperature. So if this is the dry bulb temperature is whatever, I don't know, 60, and the wet bulb temperature is 45, then you have to submit. And this green point here is that condition. And then you have all these values here. I don't remember. Okay, so you have to find the relative humidity and the dew point temperature. Okay, piece of cake, because you can go here, and this is the relative humidity and the dew point. So this is the dew point. Okay, so I want you to make this simple exercise. So you have to enter you have to click on that link you will be on that website, and then you only have to include this. So we have only two conditions, two input conditions. In this case, it's the dry bulb temperature and the wet bulb temperature. In this case, it's the wet bulb and the dry bulb temperature. Here we have a wet bulb and another dry bulb, and then you have to calculate different things. But this one is related to the enthalpy. So this one is slightly different. So here we have 1,000 cubic feet. So this is volume of moist air. We have the dry bulb temperature, yes, and a relative humidity of 60%. This is sensibly heated to a dry bulb temperature of 80 Fahrenheit. How much heat is required to complete the process? Okay, so I'm going to explain this, and then I will change the figures for that, okay? So what are we going to do? First, we have 50 Fahrenheit, the dry bulb, and relative humidity 60. Okay, so let's do this. So we are working with relative humidity, the input. So the dry bulb was 50, and the relative humidity was 60. We, this is on, we submit. There you go. We have to work with the enthalpy now. Where is the enthalpy? Enthalpy here. So this is the enthalpy. We copy 16.977. Okay, so this is the enthalpy, and this is the first thing we have to do. Second, we have to sensibly heat up to a dry bulb temperature of 80 Fahrenheit. What does it mean in the psychrometric chart? It means that if we are here, if we want to go from 50 Fahrenheit to 80 Fahrenheit, we can go horizontally here. Okay, so I have clicked here. I just moved horizontally from 50 and 60% horizontally to the dry bulb. It's 80, well, it's 80.007, but it's 80. And here the relative humidity is 20.72. And what is the enthalpy? The enthalpy is 24. There you go. Okay, so that was the enthalpy of the first point, and this is the enthalpy of the second point.
Now the heat equals volume times H2 minus H1, enthalpy 2 minus enthalpy 1, divided by specific volume. 1,000 cubic feet, this is the volume. Enthalpy 2, it's 24.17. Enthalpy 1, it's 36.9, divided by 13.7, the specific volume.